All right, so far we went from static attraction to actuators. Now we want to look at motors. The world ain't going to move without motors at all. And we have some of the, again, we go back to history about 100 years plus or so ago. Werner von Siemens in Germany. And now Siemens is one of the biggest motor power supply, electric power for the infrastructure companies on the planet. We have Zenobia Graham, back in 1826, one of the early pioneers of motors and design and using brushes to get the motor power, electric power to the rotor. Nikola Tesla, of course, Tesla was a super giant in electric power, particularly AC systems. George Westinghouse, who originally designed the brake, a very important brake for locomotives, and as an industrialist recognized the power of electric motors, particularly for locomotives, and built a fantastic company. We have over here our boy Tom Edison, and someone who not a whole lot of people know about, but was perhaps the most important person ever for giving us electric power, as we know, is a gentleman named Charles Steinmetz. A really fun dude to look up. And a little bit of industrial lore here. He's got a cigar, right? And transformers use transformer oil, and there's a lot of chemicals in electric transmission systems, the transformers. Extremely flammable. Well, Steinmetz was allowed to smoke because you don't let me smoke, I quit. He was that important. So they hired a fire marshal to basically follow the dude around. And as an engineer, he had a fantastic salary. He had no salary. He just said, look, whatever I sign my name to, you pay. What? And the accountants went all, well, we can harness that power of the accountants. Fine, then I quit. I don't need anything. So legend has it that he would row himself out in his rowboat in the middle of a lake, do his calculations, smoke his cigar, come back in, show up when he wanted to, and all this stuff worked, which is why we have all this electric power. Because his theories for AC power transmission in AC electric motors and generators, truly phenomenal. Him, Tesla, Siemens, Graham, Edison, giants who had vision and passion for what they wanted to do, all about making things spin. Better, faster motors. Many different types of motors, DC brushed motors, where you have permanent magnets on the outside and the core of the magnet, or excuse me, the core of the motor or the rotor has a winding on it. And we'll see if you can look into the inside of the motor here. You can see the copper coils that spin, and the different phases, the power gets to those different phases by what are called brushes. We'll talk about brushes in a little bit. And then you have versions of these motors where reciprocity has been applied, and there are no brushes. Can brushes wear? But you have magnets on the rotor that set up a magnetic field, and that is actuated by coils of wire around them. And then you have motors which don't use any magnets, but they induce a magnetic field with a set of coils, wire coils, that then act on another set of coils through which current runs, and they spin. That's one of your most common motors, just constant speed electric motors that drives fans, refrigerators, so much stuff we use and own. This is not a class in motor design, but there are some things that we can understand about motors when we go to design with them. You can go to a catalog and look for what you want, but a very powerful tool I want you to think about when you first start sizing a system is the following. That if I have a rotor, so this is going to spin, and it's surrounded by the stator, which is fixed, And for now, we'll assume this has coils of wire and that this has a permanent magnet. And when I put power into the coils, I'm going to cause the rotor to start to spin. We'll go in a little more detail later. And for example, the opposite of that is here is the windings, 3 windings on the rotor, and then 2 poles or magnets on the outer housing. This is actually that motor I just showed you a minute ago taken apart. The interesting thing is what is actually happening here. It's acting as if there is a shear pressure. And this I drew in 2 dimensions here. Any of these motors will actually have some length. So when I start thinking about how much torque I can get out of this motor, I can actually, before I ever go to the motor catalog, before I pick what type of motor, I can get an idea of what I can get out of it based on this size, and then based on just very first principles. And based on that, it allows me, when I'm sketching out a machine, without ever knowing any details about what motor I'm going to use, have an idea of how big the motor is going to be and will it fit in the size package I'm thinking of. And how do I do that magic? Well, it's based on, depending on the type of motor, there's a certain shear pressure I can get at this interface. And we know that force equals pressure, or this is shear, times an area. Units here would be newtons equals newtons per square meter times area. So these units cancel, you have newtons equals newtons. So this, when I apply the voltage here to the coil, it's going to cause uniform over this entire surface of the rotor, this shear, or it's going to cause it to move. I want to know what's the torque out, how much twistedness I'm getting. Well, this rotor has a certain diameter, d rotor, and torque equals force applied at a distance. So the torque out from the rotor is going to equal the force times this lever arm or radius, which is the diameter over 2, which is going to equal this shear times the area times the diameter over 2. Well, what's the area the shear is acting on? If the rotor has a length L, I now get that the torque out is going to equal that electromagnetic shear, times pi times the diameter times the length of the rotor times the diameter of the rotor over 2, which is going to equal tau 2 pi diameter squared over the length. Remember St. Vinay's principle? So your rotor length is typically on the order of 2-ish times the diameter, 1-ish, 2-ish. It's not going to be really long in general, because then the rotor can start flexing and having its own problems. So let's just say that the length goes like, we'll call it some factor gamma, times the diameter of the rotor. So as a result we get the torque output from the motor equals 2 pi, this electromagnetic shear pressure we can generate, d cubed gamma, right? Is that right? Why did I put L here? That should be a 2. I'm sorry, I confused things here. L is up top. So you got to check me. 2 is down here. Okay. Do I have everybody I need? Yep. Tau pi d squared L is gamma dr. There. I'll put my R here so you know it's of the rotor. What you'll find is when you go, as the motor diameter gets bigger in diameter, and it also grows in length, basically in the same proportion, the torque you can get out from the motor goes with the cube of the diameter. Very important scaling law. Now, for different kinds of motors, you'll get different kinds of shear pressure. So for example, and it's nice to put things in terms of atmospheres. So remember, 1 atmosphere of pressure equals 14.7 psi, if you like to use the imperial system, right? Which is, and this is at sea level at 20 degrees centigrade, 100,000 newtons per square meter, or 0.1 newtons per millimeter squared. For a typical induction motor, tau induction, I can get perhaps 0.1 atmospheres. For a really, really high quality liquid cooled, to keep the coils from burning up, permanent magnet motor, I could get up to 1 atmosphere. Most DC motors, brushless, brushed, will be, with good, relatively good heat conduction, will be somewhere around 0.2 atmospheres. So these are some very rough first-order calculations that allow you to calculate how much torque you can get out of a motor. You can get a lot of speed and hence more power by increasing the voltage. The outer sizing of this motor, you'll find that the outside of the motor housing typically is around 1.5 times the diameter of the rotor. And the length of the motor housing is typically about 1.5 times the length of the rotor. So there are some first-order proportions that will help you start thinking about how big is a motor in accordance with how much torque you can get out of the motor. Very, very important first-order scaling laws. These are the kind of things that you can also build up experience with if you're working in a type of industry and you tend to use a type of a motor. You can, as you look through catalogs of motors, start to look for what are these proportionality factors, and that'll help you thinking about what could be designed in case you ever needed a custom motor. So let's look at a very common motor, just a little DC brushed motor. And a DC brushed motor like the one we were just playing with, it's one just like this. And let's take a peek at it. And I got my trusty power supply here again. And not a whole lot of excitement is going to happen until I turn the power on. And why are we not spinning? Why is this motor not spinning? Let's try another one. Maybe we burn it out. Let's see. What is wrong? Why is the motor not spinning? Here's another one. Same motor. Why does this one spin and that one doesn't spin? What could have happened? When you take these things apart, you'll find that if you have too much current going through them, you can burn out the windings. So you can't arbitrarily get infinite cosmic power from a little bitty space. So someone tried to put too much current into the motor in order to get more torque out of the motor than it wanted to or could produce, and the little windings fried. Because remember, E equals IR, voltage equals current times resistance. And power goes with what's called I squared R. There's also, when you put more current into a motor, there's more power, and there's losses in the electric wire, the wire inside the motor, and you can create so much heat as you're trying to push so much electricity through the wire that you will literally burn up the motor and fry it. So a big limiting factor in using electric motors is often how well can you get the heat out of the motor. And that's why, for example, this motor has holes in it to the center, so as it spins, air flows through to cool it. So you have to be very careful when you use electric motors about what's called the duty cycle of the motor. What's the duty cycle of the motor, and how long does the power stay on doing what amount of work? All that goes into the analysis of the motor to figure out how well it works. Now, the reciprocal to this is, that's not enough. That motor doesn't have enough oomph for what I want, so I'm going to get a bigger motor. Okay. Whoop. So, bigger motor, yeah. Bigger motor. And trying to get bigger motor, I'm trying to interface to the motor leads. Here we go. You see, interface connectors are often going to be the bane of your mechanical, electrical existence. Yeah, now I got a power supply to drive this motor, get lots of oomph out of it. Yeah. And if that motor is not big enough, bring out Mondo. Yeah. Now we're really going to go rocking. Yeah. Yeah, let's crank this puppy up. Yeah. So now you know, yeah, you're going to get some real motor action. Yeah. Now we got it really going good. Yeah. Ain't going to burn this motor out. Yeah. Yeah. Ain't motor ain't going to move at all. Huh? What happened? Well, and I cranked it all the way up. So just like before where we said, should no work. What happened? Infinite cosmic power supply. Motor dies. And then we get infinite power motor. And the infinite power motor sees a little itty bitty power supply and says, because there's so much of a large winding in here, of coil, of wire, that this little power supply just can't, by the time the electricity goes all the way through the coil, it uses up all the current this thing can give it, and there's not enough ability to turn the motor. So what do? You've got to match the power supply's ability to the ability of the motor. The current and the voltage have to be able to work together. So this is, for example, what we're talking about. And remember, this motor from that the V-belt, timing belt discussion we had under belts. So here I've got a lithium-ion battery. Remember the drill earlier? We did the remove the skin from hand experiment. And let's just see what happens. Woo! Did you feel that torque? I did. See, what happens is that was an impulse. That was 1 volt. So you found the starting torque that happened. So I will watch while I'll stop the motor from turning. Not. This is the inertia of the system that makes it take off and action and reaction. So now we're going all the way back to topic 3, Newton's laws. So when you design a motor and you want more infinite cosmic power out of it, you got to remember that the system to which it's attached to is going to have to be able to not only take the load at steady state, but the transients. Those are the instantaneous, and it's those transients that often cause an instantaneous huge load in your system where it causes most of the damage to the system. System. There's that word we were talking about before earlier. Remember the mechanical part, the electrical part, and the controls part. Okay? So, where do you use the motor in its operating regime? How much initial torque do you get on it? And if I had a good control system, such as with the drill, where I wouldn't suddenly dump all the potential of the battery into the motor, see, I would have a control system that starts it up slowly, slowly build the torque, and go all the way. You don't want to just, okay? So how you put the power into your machine, big effect on the life and the quality of the machine. Now, gear motors tie in the transmission directly with the motor, and they often come in a package, or you assemble it. So this, for example, is a gear motor. High velocity, modest torque electric motor. Then this is a planetary gearbox. The output of the shaft of the gearbox goes to, in this case, this pulley. And now watch this. I can take this and back drive it. And notice when I first start applying a torque, I'm applying a torque and nothing's happening. And then it breaks away and it's even. Part of that is due to resistance in the gearbox. Part of it is I'm back driving the motor, which initially acts like a brake. And let's see if we can run this experiment this way. This is a lot harder to back drive because when I'm back driving, the motor is acting like a generator. And if you short the leads on a DC motor, then it tends to act like a brake. So when you're buying a gear motor, remember our earlier discussion of optimal transmission ratio, and when it's a modular stage of a planetary gearbox, and recall from topic 4, the nice thing about planetary gearbox is you can just keep adding linear stages where the output of one stage, the sun, drives the planet carrier of the next stage. The planet carrier of the next stage, its output then goes to, you can see here, one drives another and you stack them all up. Each stage giving you a higher and higher gear ratio. I'm sorry, the sun from one stage drives the planets on the planet carrier of the next stage. The planet carrier connected to the planets then spins and it is attached to the sun of the next stage. So you can get quite high gear ratios. The key to the efficiency of being able to backdrive this machine with a planetary gear ratio, by the way, is how carefully all the elements are aligned. Very, very important. Precision alignment of the gears will help, well, actually will directly, greatly affect the efficiency of the gearbox. And you know you have a pretty good efficiency gearbox, or you've assembled it properly, when you can backdrive it. And if there's any misalignment problem, you can feel the crunchies that you would happen. This one was assembled very nicely. There's very little crunchies. And if at any one point it's tight, you would notice a tightness in it. This one is actually smooth all the way around. The human tactile feel is a fantastic quality indicator, actually. Now, where do I run my motor from? What gives me the best power? So a DC motor, by the way, has what looks like the torque speed curve like this. very high torque. Ah. 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 You will stop. Okay, there. A lot of torque. Oh, ain't no speed. Something's burning. I think I'm burning up my motor doing that. That's okay. We'll get another one. If you have very high torque, no speed, that's not spinning, drawing a lot of current, not spinning, no airflow over it, and is the dog in here? Nope, you're burning up your motor. So, bad. On the other hand, infinite speed, no torque output, it ain't doing nothing for you. There's something in the middle that will give you the most power to do the job most efficiently. And it turns out, in all this mess of lines, that nominally about every motor has what's called its most useful operating region, where you're running at about half the torque and half the output speed. That's the ideal power output. And in reality, you're running about, if you want to have very long life, long duty cycle, doesn't overheat, you're going to get about a quarter to a third of the maximum torque out, and you'll get somewhere around half the maximum speed. So when you look at what a motor is rated for, you have to be very careful to look at, is it the peak torque or the continuous operating duty? How often you take the torque out of it and for how long will depend upon whether it's going to burn up or not. Okay, so in addition to the optimal transmission ratio, there's the optimal speed at which you're going to operate the system at in order to get the optimal power transmitted to the load, and that's about half of the no load speed. So when you look at a motor and it says no load speed 10,000 RPM, in general you're then going to say, okay, I'm going to be running at about 5,000 RPM. Okay, so look for these torque speed curves for the motor and recognize that this is the type of operating region you're going to be in. There's a tendency amongst designers to say, oh boy, no load speed, 10,000 RPM, and then, oh boy, look, peak torque, 100 Newton meters, and then assume, oh boy, I can get 100 Newton meters at 10,000 RPM. No. Peak torque means no speed, which we just saw is not a good thing, but that is the peak, for example, to get you started at no speed, and then as you ramp up in speed, you don't need so much torque anymore. Okay? And of course, there's a design spreadsheet that goes through what the motor can do. The first order sizing based on the equations we talked about earlier, the transmission ratios, the inertias, what's the optimal transmission ratio. So this is all contained in a spreadsheet that we'll go through at a later date, or you can try writing your own based on the formulas you find in the text or the internet, because it's all very straightforward. The key is how you organize your information, present it, and use it in a manner that you understand. Very important. You may want to do fancier things where you're also calculating the inertias of the elements that you're driving in order to match the optimal transmission ratio. You may want to interface with a solid modeler to get the inertia out. You can do all kinds of fantastic, we call it design automation, where you're helping to automate the design process. So you do the creative part of the design, and the calculations that you figured out and stored in the software then follow through on the calculations. Because remember, you can put stuff together that works, oh boy, that was exciting, but when you go to have a product where you want to sell thousands or hundreds of thousands or millions of the product, if you don't have enough oomph, people won't buy it. If you have too much oomph, that means you're wasting money, wasting resources. So you want to be able to put in just enough oomph. Similarly, when you have the design tools worked out, you can simulate the performance of your machine before you actually build it. So we like hacking. We like putting stuff together to generally learn about the principles of things. But once we understand basic principles, it's a lot more fun, actually, you'll find, to hack, quote, hack, by first do as much of the analysis as you can to get you there as quickly as possible. This is tying back to topics 1 and 2, the appropriate analysis. Appropriate analysis are things like the equations I did here for the initial sizing. So when you go to put together your machine and you run it for the first time, you've got a pretty good chance of it actually working the way you want. Because remember, time is money, and whether you're working in a class for a robot contest or your job, you've got to minimize the time from, I got to solve this problem, to, yeah, check it out, that's working really good. Yeah, that's good. Yeah. Okay, very important. Oh, all these equations and everything else. Oh boy, that's tough. Yeah, okay, but I can do it. So what's the real hard thing about designing electric motors? Cables. And I'm not being facetious here. You saw the problem I had connecting with this guy. And here's this little motor here with these little tabs that I had to straighten one out. How many times can I straighten out before it breaks off? Or earlier with my solenoid, I don't know if any of y'all noticed. Let's see, where did I put it? It had little itty bitty leads. Ah, here they are. So check out the leads on this dude. What is going on with that? Well, it turns out it used to have nice long wires, but the nice long wires, they got broken off. So you can have the most beautifully engineered machine. Oh, that's so nice. Oh, boo, moves exactly the way I want. Oh, yeah. And spaghetti leads, a rat's nest of wires, and as the machine moves, the wire from the motor, if it's going, eventually that, it's going to break off. It's absolutely critical and key when you design with electric motors to have strain reliefs. Notice here what's happening. The wires come out of the motor, and it makes a loop on the motor coming away, and this is a piece of electrical tape. So if I'm wiggling the wire here, no force is put on the connection into the motor. This is a very crude version from a simple little design contest. But the moral of the story is the same. When you're designing electric motors, solenoids, anything wires going into it, you use what's called a strain relief, such that any motion on the wire doesn't cause motion of the wire into the motor, because that's where you'll break it. Okay, really critical. Similarly, if you're using one of these gear motors, as we've given examples in the past, you don't do stuff like this. You don't have a gear way out in the end of the shaft, such that when remember the gear teeth, when they mesh, there's a separation force that pushes them apart. That's based on the pressure angle of the gear. If you don't remember that, go back to topic 4. You never want to do this, because you'll have a large force applied here, many shaft diameters away from the support bearing. St. Venant's principle is violated, and you'll very quickly wreck the output bearings on your motor. Okay? So beware of how you put things together. Look at this situation here. This person has, and this is actually right from the catalog of this motor company. They show, this is a sprocket for driving a belt, and look how far out. This is where the load on the belt would be. Because remember, you've got, for example, a sprocket to a load. Here's the torque output from the motor. This is the radius of the shaft. So for this belt to work, it pulls. You're pulling, just like when you're on your bike and you're cranking. And that's a huge tension in the chain, based on the torque on the crank, climbing up that hill. And this torque is creating a force in the chain, where the force in the chain equals the torque from the hub divided by the radius of the hub. Oh, there's a force acting here due to the torque of the motor. Look at the diameter of the shaft and how many shaft diameters away from the first bearing it is. It's about 3 shaft diameters. You say, well, Sanjay says that's okay. But look at the spacing of this bearing. It's just one bearing in the tip here. That's it, actually. And then the other bearing, it's actually acting on the sun gear. So when you push here, this shaft twists and misaligns the gears. You want the forces to go, ideally, right through that support bearing and not put any moment on the shaft at all, such as this kind of design here. Even if it means doing a counterbore in your gear to put it in tight such the gear tooth forces really act as close to that bearing in the motor as possible. And indeed, when you buy a gearbox, or a motor gearbox, they'll often have a limit of what's called the shaft overhang load. That tells you, as a function of distance along the shaft, how much radial load it can take. So beware of these two things. You may have designed the most brilliant, beautiful, balanced, optimal system, and if you don't get the wires right and how the loads are taken out from the motor from the shaft, ain't going to work very long. So, where else can you learn about these systems? Hint, hint, hint. Take stuff apart. And when you take stuff apart, look at it critically. Not necessarily, well, I took this thing apart, and you know what? They use their shaft, blah, they overhang those. Slocum's principles is fundamental principle. That's not true. I took this thing apart last week, and it didn't. St. Vinay's was wrong. Rawr. Well, dude, why'd you take it apart? Well, it broke. So, a lot of things take apart because they're obsolete. A lot of things you can find that were thrown out in the hallway for you to take apart because they broke. They don't work no more. Find out why they don't work. What happened to them? And this little case study of a CD drive, this will still work. This is a very well-designed product with fantastic tricks of using flexures to create the preload you want. Remember we talked about that in the context of flexural linkages, of using screws, multiple stages of gears. Here I've got 2 helical gears engaging. Why do they use helical gears here? Well, because you use a helical gear, they tend to create an axial force which creates a preload. And remember we talked about the torsion differential, how it self-locks up with the torque to the wheel that needs it, by using that property of self-help. Remember that from topic 3. These gears, helical gears, when they engage very smoothly, but they create axial forces to make them move axially as well as radially, I can use that force as for good. Remember, whatever you may think is a, quote, problem, you can turn into an opportunity. And one of the best ways to learn about these things, yes, you can read in the book, blah, 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 is to take things apart, feel them. The tactile feel of mechanism helps you to hardwire your brain so you can be a better designer. Doing first-order calculations on why is that size that way? Why are these teeth this way? What is that transmission ratio? Go and do the calculations to try to figure out what they did and why. That's all part of the process called reverse engineering. Reverse engineering is starting with something that was done, going backwards systematically through it and trying to figure out why it was done and learning from that process. It's also a lot of fun to take stuff apart, and sometimes even to put it back together.